Okay, the recording is going. So for the most part, I want to leave your learning about this to the textbook and the notes that I wrote up and the video lesson that I posted, both for momentum itself and for dealing with collisions. But I am willing to go over a little bit of an introduction so that we have a starting point here. Momentum is a variable which is letter P. I don't know why we use the letter P for momentum, but that's the letter that we use. And it is equal to the mass of an object times its velocity. Now, velocity is a vector, so when you multiply by mass, the result is a vector. That is, momentum is a vector. And one of the reasons we like momentum is that for a single object, the change in momentum is determined by force. It is F average times delta T. So if you exert a force on an object for some period of time, then you are giving that object some momentum. Now, whether the object moves because of that depends on whether there's other forces. You know, if you push on a wall, there are other forces that come up that make the wall not move. But if you push on a cart, then your act of pushing gives the cart some momentum, and then the cart will have some velocity after you push it. And this quantity here is called impulse. Which is often a capital I. If you're a science fiction fan, you may remember that in Star Trek they have impulse engines and warp engines. Well, impulse engines come from this idea of impulse. And part of the idea of an impulse is that the amount of force you need to get the velocity, and the velocity is directly related to the momentum. So the amount of force you need depends on how much time you exert the force. You could exert a really strong force for a tiny bit of time, or you could exert a gentle force over an extended period of time. Either way, you can give the object the same amount of momentum and achieve the same final velocity. So impulse engines would presumably be shooting little bits out the back, which would mean exerting a force on the little bit out the back, and that force is equal to a forward force on the vehicle because of Newton's third law, and thus exert a large force for a tiny bit of time, giving your spaceship a little propulsion. Now, for many objects, it makes sense to talk about the total momentum, which would just be the momentum of object 1 plus the momentum of object 2 plus ... If you had more than 2 objects, you could add in more than 2 momentum values there. And the reason that this is interesting is if object 1 and 2 exert force on each other, then F12 is equal to minus F21. That is the equation form of Newton's third law. If I push on the wall pushes back on me, and I can feel that in my hand as I push on the wall. Well, if we just multiply both sides by delta T, that means that delta P2 is equal to minus delta P. So this force that's exerted between 2 objects takes momentum from one object, takes it away as a minus, and gives it to the other object. Every force involves an exchange of momentum between 2 objects. And that means that if we write this as delta P1 plus delta P2, we can get this equation just by adding delta P1 to both sides of the previous line. That's got to be 0, which means that P1 plus P2 is constant. So if this is the only force causing the momentum to change, then this is the amount of momentum change that each object will have, and the total momentum of the two objects, P1 plus P2, is going to end up being constant. And that's one of the principles that we use in collisions very frequently. Yes. So let's say a 75 kilogram is standing on a skateboard, and they throw a 0.5 kilogram ball forward with, let's see, how fast can a person throw a baseball? Let's go with 25 meters per second of velocity. What does this do to the person? So initially, we have M person and M ball, and P total is equal to, we should take mass times velocity for each individual object and add them together. So we would have mass person V of the person plus mass of the ball V of the ball is equal to 0, because both velocities are 0. In the final state, that is after the person throws the ball, we're going to have mass of the person and mass of the ball, and we'll have V ball equals 25 per second. So we can write P total is equal to mass of the person, V of the person, plus mass of the ball, V of the ball. And this time, instead of just doing a calculation, we need to fill in everything we know and see what we have to solve for. So one thing we get to do is we get to put a 0 in here. That is this 0 up there. That's the idea of conservation of momentum, that the total momentum before the collision is equal to the total momentum after the collision. So if I know the total momentum before the collision as a number, the number 0, I just plug that into this equation as the total momentum after the collision. And then let's go in and put a 75. The person, well, we're not told the velocity of the person, so we can't put anything there. And then mass of the ball is 0.5, and then the speed is 20. Now we have an equation in which everything is a number except for the speed of the person. So that means we can solve for the speed of the person. So this would be minus 0.5 times 25 equals 75 v of the person. So then we can just go over 75, cross that out. Divide both sides by 75 to get rid of it. So now we have an expression for the velocity of the person, and that comes out to minus 0.1677 per second is velocity of the person. So I can take this result and put it in the diagram here as the person goes backwards. So throwing that light ball forward quickly gives the heavy, as compared to the ball, I'm not being judgmental, person some backward velocity. And this is the idea of recoil. It's often discussed in terms of guns. Shooting a gun in the forward direction causes some recoil in the backward direction. But it's true of just the act of throwing as well. Now, question. Why don't I tend to notice this when I throw a ball? Well, probably because I'm standing on the ground. So instead of that force of throwing, so I throw the ball forward, so it exerts a force back on me. Instead of that backward force causing recoil, instead that backward force causes static friction to occur on the ground. And I push backward on the ground, and the ground pushes me forward. So the backward force from the ball and the forward force from the ground cancel each other out, and I can stand still and throw a ball. So that's the most basic example of conservation of momentum that I can think of, which is slightly different from the one I did yesterday. And hopefully that will help you understand a little bit more about momentum.